All right, you guys. So today we're just going to talk briefly about the weighted average atomic mass and how to find it. You'll hear me refer to weighted average atomic mass as WAAM, not to be confused with the 80s duo WAAM, who were incredibly fabulous, and you should look them up if you're not familiar. The WAAM is calculated by taking the mass of isotope 1, multiplying by its percent abundance, plus the mass of isotope 2, multiplying it by its percent abundance, and so on and so forth for as many isotopes as you have. And then you can divide that by 100%. If you want to simplify it, the way I usually do it is I just turn my percentages into decimals. So I have the decimal of the percent abundance, and then I do the same thing. So I'll multiply the mass of isotope 1 by the decimal abundance of 1 plus the mass of number 2 times the decimal abundance of number 2, and so on and so forth. But either way you do it is just fine as long as you know what you're doing and why you're doing it. All right. So this is a quick practice of something you should already know how to do based on the POGIL yesterday. So you should take the mass number from the isotope symbol and use that as your mass of your isotope. And then it's asking you to calculate the weighted average atomic mass of lead. So you're going to use this data of its 4 isotopes to calculate the WAAM of lead. Please pause the video and try to work this out for yourself. Okay. So whenever you're finding the WAAM, you can always double check your answer by looking at the periodic table. And so if we look at the periodic table, it says that the weighted average atomic mass for lead is about 207. And so we're hoping that our answer came in around that ballpark. So here, I just have a quick solution, and you can see I've taken the mass number, 204, I've multiplied by the percent abundance, written as a decimal, and then I added the mass number of the second isotope times its percent abundance as a decimal, and so on and so forth. And then I multiplied out and simplified, and then I added each of those answers together to give me 207.19 atomic mass units. So that checks out, that matches with what we have on the periodic table. So that's a good thing. Here's another example. There are 3 isotopes of magnesium along with the composition of its nucleus and the relative abundance. Use this data to approximate the WAAM of magnesium. So if you have the protons and neutrons, right, you can find the mass number. So that's the first thing you're going to do is find the mass number for each isotope, and then you can solve for the WAAM. And apparently I did not make a solution slide for that one. Yeah, I did. There it is. That's so weird. Anyway, so you can see I just added the protons and neutrons to get the mass number, and then I multiplied by the decimal of the percent abundance for each one. And so that ended up, when I simplified it, I got 18.96 plus 2.5 plus 2.86, and then that gave me a total of 24.32. If you look at the periodic table, the WAAM of magnesium is listed at 24.3, and that is close enough for me. All right. A little chemistry humor for you. What did the scientist say when he found 2 isotopes of helium? Get it? Because helium's symbol is He, and there are 2 isotopes, so it's 2 symbols. Okay, cool. There are some different iterations of how you can use the WAAM formula to find different information about isotopes. So data for the 4 isotopes of chromium is listed below. Use this data to calculate the mass of the missing isotope. So we've got chromium 50, chromium 52, unknown chromium and chromium-54. And we know that 49.95% of chromium, or sorry, that's the mass. I was like, wow, those don't add up to 100. 49.95 is the mass of chromium-50, 51.94 is the mass of chromium-52, and 53.94 is the mass of chromium-54. The relative abundances are 4.345, 83.789, 9.501, and then 2.365. And then we know the WAAM is 51.996. So that allows us then to try to calculate that missing chromium mass, because we have only one variable. And so we can solve for that. So when we set it up, it's going to look like this. Right, so here's my WAAM that I'm given, or you could pull it off the periodic table, 51.996, and then the mass of my first isotope, 49.95, times its decimal percent abundance, 0.04345, and then I do that with the second isotope, that's in green. And then the third isotope is the one where I'm missing the mass. So I just substituted in an X and I made it red, so we'd know that's what we were solving for. But it's still multiplied by its percent abundance. And then in purple we have that last isotope of chromium. So we start to simplify this. We want to just collect our like terms and start to simplify it down. So I just multiplied everybody out to make these individual numbers. Now I'm going to collect like terms by adding all my numbers without a variable together. And so that's going to look like this. So now I have my percent abundance multiplied by my unknown plus the sum of all of the contributions from the other isotopes, and I'm going to subtract 46.966 from both sides to isolate my variable x. Now I have 5.03 is equal to 0.09501, and now I can solve for x by just dividing both sides by 0.09, and then that gives me 52.94 AMU for my variable x. Okay, what? This is so weird. If I click with the mouse, it skips 2 slides, but if I use the arrows, it skips 1. Anyway, here's a practice problem. Go ahead and try to find the mass of the missing iridium isotope, and then on the next slide we'll be able to look at the answer. So pause the video. Okay, cool. So if we look at this one, it's a little bit simpler. I only gave you 2 isotopes instead of 4, but we have the isotope of iridium at 191.04 and its abundance is 42.0. Then we have an unknown isotope with an abundance of 58. Notably, the abundance adds up to 100. That should always be the case. So just keep that in the back of your mind as a way to check for mistakes. And then the WAAM, which can be given or you can just look on the periodic table, is 192.2 atomic mass units. All right, so I've got the WAAM is equal to the mass of isotope 1 multiplied by its decimal abundance plus the unknown mass of isotope 2 times its percent abundance as a decimal. I'm just going to kind of simplify down. So I multiply the first isotope together to get 80 plus 0.58x. I'm going to subtract from both sides to get x by itself, and then I can divide both sides by 0.58 to get x by itself, and so my missing isotope has a mass of 193.04. Alrighty, so the other type of problem we could have, which is a little bit more complicated, is finding the relative abundance. And so here we see gallium has 2 isotopes, gallium-69 and gallium-71. Find the relative abundance of each of these given the mass of each isotope and the atomic mass. So the WAAM is 69.723, and the mass is about 69 and about 71. So we need to set this up and solve for the relative abundance of gallium-69 and gallium-71. And, you know, right off the bat, I'm starting to think, interesting, because I have two variables. So if I start to think about this and set it up, I have the WAAM is equal to the mass of the first isotope times the percent abundance, which is unknown, so we'll call it X, plus the mass of the second isotope, which is 70, times its abundance, which is also unknown, and is Y. And it's possible that X and Y are the same. It could be 50-50, but it's probably not. And so that's why we have to use two separate variables, because it's very unlikely that the percent abundance of both isotopes will be exactly the same. Okay, so now I'm just going to kind of simplify that, get all the brackets out of there. And I notice that I have these two variables, and I really need one variable to be able to solve the problem. So we got to think about what has to be true about the percent abundance of the isotopes in order to solve this equation. So the key here is that all the percent abundances have to add up to 100%. And if we're thinking about it in decimal notation, which is what I prefer, then they have to add up to 1. So we can write about our variables, x plus y must equal 1. And that allows us to redefine y in terms of x. So y is actually equal to 1 minus x. And by creating this kind of system of equations, we can use substitution to solve for our variable x. And see why the Algebra 2 requirement's in here now, can't ya? Okay, so back to our original equation, 69 equals 68x plus 70y. And now we're going to substitute in that y equals 1 minus x. So that looks like this. So we've got the same equation, but instead of 70 times y, we have 70.92 times parentheses 1 minus x. So first step is just to distribute this out. And I went ahead and just changed x to red, so it's a little easier to keep track of our variable. We have now to collect like terms to simplify this down a little bit, and we wind up with negative 1.99x plus 70.92. I'm going to keep trying to isolate my variables, so I'm going to track 70.92 from both sides, and that gives me negative 1.197 equals negative 1.99x. Divide both sides to solve for x. And so that gives me 0.6015 equals x. And so if I multiply by 100, then that percentage would be 60.15% of the sample is the first isotope that weighs 68.93. So now that I know that first isotope, and I know it has to add up to 100, I can just say, all right, 100 minus 60.15 is going to give me my 39.85%. We've got a couple of practice problems on here. Go ahead and pause this and work it out. Okay, you can see here we use that same system where we just substituted 1 minus x in instead of having x and y. And so you should end up with 7.59% lithium-6 and 92.41% lithium-7. Here's another example. Work that guy out. And you can see as you work through it, you should wind up with 48% europium-151 and 52% europium-153. And that's all she